Hey there, it's Shannon Matthew Myers. Tonight, it's nighttime where I am. We're covering reflexivity, symmetry, and transitivity of relations. So let's warm it up a little. This is something that you would have done in the 8.1 assignment. So let's, if you want, go ahead and pause the movie and check out what you get. All right, let's see how you did. We want to create the directed graph for the following relations. So A, the set A, has elements 1, 2, and 3. And the relation R on the set A is for any x and y belonging to A, x, r, y, if and only if x is less than or equal to y. Okay? So, all right, well, let's just see what R would equal to. So R would equal to the set 1, 1, because 1 is less than or equal to 1, 1, 2, 1, 3. Cool so far? All right, and then starting with 2 as that first coordinate, we would have what? 2, 2, because 2 is less than or equal to 2, and 2, 3, because 2 is less than 3. Good so far? Okay, so let's check it out, all right? I think we have all of our ducks in a row here. So let's make our directed graph and check out what it looks like. We've got 1, 2, and 3, right? And if we look at the ones, 1 is related to itself. 1 is also related to 2. And 1 is related to 3. Cool, cool? All right, and then when we look at the 2's, what do we have going on? Good, we'll have 2 is related to itself, and 2 is related to 3. Cool, cool? All right, so now we'll come back to this one. This would be our answer. This is our directed graph, and this is this set here is the relation R on A. And so let's look at some definitions. It turns out that R is reflexive, and you, of course, need to know these. If and only if, for any x belonging to the set A, x are x. Cool, cool, cool? All right. So in this case, do you see how 1 relates to itself, right? Because 1 is less than or equal to 1. 2 has a directed arrow to itself, but 3 doesn't have a directed arrow to itself. So we know that this relation is not reflexive, since 3 does not map to 3. Okay, well, R is symmetric if and only if, for any x and y in the set A, sorry, this is a typo, thought I got them all. If x are y, then y are x. Well, here you basically have to have arrows going both directions. And you see that we don't have this for anything. 1 goes to 2, but 2 doesn't go to 1. 2 goes to 3, but 3 doesn't go to 2, and so forth. So R is also not symmetric. And remember, when something's not true, you only need to provide one counter example, right? So we'll write this one a little bit differently. Let's use the example that 2, 1 is not an element of R. That's a same way of writing 2R3. Okay, well, what about... Okay, so R is transitive if and only if, for any x, y, and z that belong to the set A, if x maps to y and y maps to z, then x also has to map to z. So this one can be a little bit more forgiving because of the fact that we have it only if the first two are true, then the third has to be true. So let's see what we've got. 1 maps to 2 and 2 maps to 3. So 1 would have to map to 3, and hey, guess what? That works. So I think we're good to go. I think this one is indeed transitive. R is transitive. Now we'll be talking about some other problems, and when we do those problems, we'll go a little more in depth when something is true. But this is just to give us a big picture idea. There's equivalent ways, of course, of saying these things or writing these things. So R is reflexive if and only if for any x belonging to a set A, the ordered pair x comma x belongs to the relation. R is symmetric if and only if for any x and y belonging to the set A, if x, y belongs to R, the relation, then yx also belongs to the relation. That gives us symmetry. And R is transitive if and only if for any x, y, and z that belong to our set A, if you have if x and y and z belong to the relation, then good, x and z also belongs to the relation. Cool, cool? All right, note, since these are all universal statements, the negations will be what kind of statements? Beautiful, existential statements. All right, so now going on to example 2. Determine whether the given relation is reflexive, symmetric, transitive, or none of these. So for the first part of number 2, why don't we go ahead and make a directed graph, right? It's a lot easier to see if you have the benefit of having all the relation as ordered pairs, you might as well make a graph. So we've got what? We've got a 0, a 1, a 2, and a 3. Okay? So 0, 1, 2, and 3. So 0 maps to itself. That's the first order pair. Actually, do it more on the outside. 0 also maps to 1. And that's it for 0. Okay, and then 1 maps to itself. and 1 maps to 2. And that's it for 1 as the first coordinate. And then we have 2 mapping to itself, and 2 is going to map to 3. Good so far? Is R reflexive? What do you think? Well, remember, with reflexive, what has to happen? We would have to have these little circles at each of the inputs, right? So 3 is not part of the set, right? So we can say no, since 3 is not an element of our relation R. Good so far? So all we have to do is provide a counterexample. All right, so next up, let's see what we've got going on. We have, is R symmetric? So what do you think? Well, wouldn't we have to have double-ended arrows, right? So you can start wherever you want. Let's just say that no, 0, 1 belongs to R, but 1, 0 is not an element of our relation R. So that's a no. What about transitivity? One counter example is, do you see how 0 maps to 1, 1 maps to 2? So that means that 0 would also have to map to 2, but it doesn't. No. Zero, 1, and 1, 2 belong to R, but 0, 2 is not an element of R. Groovy? All right. So sorry, there's a typo here. This should not be X, R, Y. This should be C, because we're talking about the circle relation on the set of real numbers. So over here, our set is the set of real numbers R that the X's and Y's have to belong to. But this here is our relation part. Okay, cool. So, is C reflexive? Well, you can take any real number, right? Any real number that, at all. And there are infinitely many counterexamples where that number squared plus itself squared again is not equal to 1. So, for example, for our counterexample, we could say 1, C, 1. What about that? It's not true, right? Since 1 squared plus 1 squared equals 2, which is definitely not equal to the 1 that we're interested in. So we're good there. We've got our counterexample. Okay, is C symmetric? Well, yes, right? Because addition is commutative. So here we want to do this in general. And remember, for symmetry, that's only talking about all these infinitely many ordered pairs that are on the circle. Remember, for symmetry, if the ordered pair X and Y is part of the relation, then the ordered pair YX is part of the relation. So, let's think about this. Well, let's let X and Y belong to the real numbers. X squared plus Y squared is equal to Y squared plus X squared, right? Since addition of real numbers is commutative, right? And YCX if and only if y squared plus x squared equals 1, which is true. So, thus, yx is an element of our relation C. And we're done. All right, what about transitivity? What do you think? I don't think so. Because I'm thinking of 1 and 0, right? So we know that this relation, the circle relation, is symmetric, right? So don't we know that 0, 1 belongs to C and 1, 0 belongs to C, but 0, 0 is not an element of C. So thinking about this, just to expand on a little, I mean, isn't it true that 0 squared plus 1 squared is equal to 1? And 1 squared plus 0 squared is equal to 1. So those are both part of the circle relation. Well, what the transitive property says that if 0 maps to 1 and 1 maps to 0, then 0 should map to 0, right? But 0 squared plus 0 squared is equal to 0, right? So, and that, of course, does not equal 1. Cool, cool? So that's our counterexample. All right, so let's check out the next one. Let's say that O is the relation defined on Z, which is the set of integers, as follows. For all m and n belonging to the set of integers, m, o, n, if and only if m minus n is odd. Okay? So what do you think? Is R reflexive? Well, one thing to think about here, first of all, what does reflexive mean? So it means that if m was equal to n, right, then what would you get? You'd get 0, right? So you can pick m to be anything, right? Would you agree that if we let m equal to 1, which is definitely an element of our integers, well, 1, 1 is not an element of O, since 1 minus 1 equals 0 equals 2 times 0, which is even, right? Cool, cool? All right. Is R symmetric? Well, let's think about it. I'll say yes here, and we need to show that for all m and n belonging to the set of integers, if mn belongs to the relation O, then nm belongs to the relation O. Okay, so that's the plan. So let's think about what's happening. Proof. What do we know? I mean, in order for this m and n to belong to this relation O, what has to be true? Good. M minus n needs to be an odd number. And the way we make an odd number, represent an odd number in math, is how? 2k plus 1, where k is some integer or whatever letter you want to use. So let's do our setup. Why don't we let m, n, and k belong to the set of integers such that m minus n is equal to 2 times k plus 1. That's just so that we have an odd result, okay? So now let's work on this a little. So we know m minus n equals 2k plus 1. Well, what if we multiply both sides by -1? Just using algebra. Well, that means we'll get -m plus n is equal to -2 times k minus 1. Good so far? Well, remember, we want 2 times some integer plus 1, don't we? So in order to make that happen, we do some algebra tricks. So I'm going to commute the n and the -m, okay, to put it in the format that we want. I'm going to bring the 2 out. So the first part is easy. I can just have -k, right? Because I need to match this term here, the -2k. I want to have 2 times something plus 1 because that's the format we want. So remember that I need an end result of -1. If I adjust this by -1 and you visualize it, multiplying it out and simplifying it, do you see that the expression I just wrote down is equivalent to -2k minus 1? But it's in the format that we want. So we can say since -k minus 1 belongs to the set of integers, and that's because the set of integers has closure. Well, since that is true, we know that n minus m is also odd. Thus, m is an element of the relation O. Cool, cool? Okay, we're done with that one. What about transitivity? So this one here is going to be a no. Because if we think about it, if one number maps to another number and that number maps to something else, then that first number needs to map to the last number, right? Well, isn't any odd number minus 0 odd still, and vice versa? So for a counterexample, we know that 0, 3, right, and 3, 0 belong to our relation O, but these would have to, this would imply, if we had transitivity, that 0 mapped to 0, right? But 0, 0 is not an element of O, since 0 minus 0 equals 0, which is even. Okay? All right. Next up, let's look at some other proofy things. So here we go. Assume that R and S are relations on some set A. Please prove or disprove each statement. So for in part A, we're just dealing with R. There is no S. We're going to let X, Y, and Z belong to this set A. We're also going to suppose here that x and y belong to, xy belongs to R inverse, and yz belongs to R inverse. Good so far? But by definition of inverse relations, if we kind of work backwards, wouldn't it be true that z, y, and yx would belong to R? Okay, so far? But since R is transitive, what can we say here? We have z mapping to y and y mapping to x. So therefore, the ordered pair z, comma, x is an element of R. And then going back to the definition for inverse, that means that xz is an element of R inverse, and that's what we were supposed to show. Cool, cool? All right. Next step. If R and S are reflexive, then their union is reflexive. So this one's kind of cool because we bring, some basics about set properties into this as well. So, proof. Let's let X belong to the set A and let the relations R and S be reflexive, because that's in our premise statement, right? Well, what do we know if we just look at X belonging to A, and we know that from, the original assumption right here, assume that R and S are relations on a set A. And so we know that a relation on a set that's reflexive means that what? Since R is reflexive, isn't X comma X an element of R? So by definition of union, what do we know? That ordered pair XX only needs to belong to, or one of the relations to belong to the union of the relations. So by definition of union, X comma X belongs to R union S. All right. Okay, so we just have a couple more things to do here. Another definition, let A be a set and R a relation on A. The transitive closure of R is the relation R to the RT, where T is in the exponent, on A that satisfies these three properties. So RT has to be transitive. Okay? And R is a subset of RT. And if you have some other set, S, right, that's transitive, that it's also a relation. So if you have a transitive relation S that contains R, then RT would be a subset of this S. Okay? So every element in RT would be in S as well. So what is this saying? Transitive closure of a relation is the smallest transitive relation that contains the original relation. Okay? So let's do an example and check it out. Now, I got to tell you, when you're sort of building this, finding the transitive closure of a set S, it's going to be easiest to start with the second property. So we're going to do that. Okay? So here, okay, S is a relation defined on A equal to 0, 1, 2, 3. So we have S being all these ordered pairs, 0, 0, 0, 3, 1, 0, 1, 2, 2, 0, 3, 2. Find the transitive closure of S. That's this ST. All right. So we're going to look at property 2 from above, right? So that's saying that your relation is a subset of your transitive closure relation. So what does that mean? That means that every single one of these ordered pairs are also going to be in ST. So we know that 0, 0, 0, 3, 1, 0, 1, 2, 2, 0, and 3, 2 are a subset of the transitive closure of S. Cool so far? But you have to have transitivity, right, going on. So let's go ahead and make the directed graph, okay, and then kind of scope out what we need to do in order to make it transitive. And so you just want to stay organized, in this. So let's do 0, 1, and what do we have? 0, 1, 2, and 3. Okay, so 0, 1, 2, and 3. Cool so far? Okay, so we know that 0 maps to itself. 0 also maps to 3. Cool so far? Okay, let's work on where the ones map. So we know that 1 maps to 0. So it goes this way. And 1 maps to 2. And that's all for 1. What else do we know? The 2 maps to 0. And then what about the 3? The 3 maps to the 2. All the other ones are so pretty. Let me redo that one. Okay, so we got that going on. This is the weird part. ST, the transitive closure of S, has to be transitive. So if we have, kind of this connection of things, right, then we have to make it work. So we have to add ordered pairs as elements to this transitive closure of S. So, but only if you already have that 2 of them that are connecting. So for example, do you see that 0 is going to 3 because the arrow's going that way, and 3 is going to 2. And so what does that mean? That means that 0 needs to what? 0 also needs to go over here to 2. So we got to add that to our set. So we need to add 0, 2. Cool, cool? All right. Next up. Okay, so let's check some of the others. 1 goes to 0. 0 now goes to 2. So 1 has to go to 2, and we already have that. So we're good there. Okay, so now let's think if that changed anything in our, in our relation. So far, I don't think so. So let's go on to the ones, right? So we know 1 goes to 0, right? And 0 goes to 3. So 1 goes to 0. And 0 goes to 3. So 1 has to go to 3. We need to add 1, 3. Cool, cool? Let me make this one prettier. So we now have this one happening. Okay, so let's see if that changed anything. So let's look at the 2's now. Let's look at the 2's now. So we know 2 goes to 0, right? And 0 goes to 3. So that means what? That means that 2 has to also now go to 3. So we need to add 2, 3. 2 goes to 0. And 0, remember, now goes to 2. And so that means that 2 is going to go to itself. So we're also going to have to add 2, 2. And now let's check out the 3's. 3 goes to 2. 2 goes to 0. So doesn't 3 have to go to 0 now? So we basically have 3 to 2, 2 to 0, right? So that means that 3 would have to go to 0. Okay, so we'll have our 3, 0. We already have 3, 2. Let's see what we've got going on now. 3 goes to 2, right? And 2 goes to 3. And so doesn't 3 have to go to itself? So that'll give us 3, 3. And so I think actually we have everything. I don't really see any other relationships here. Let's list our result. So ST, or the transitive closure of S, is the set 0, 0. I'll just kind of intermix them. 0, 2, 0, 3, 1, 0, 1, 2, 1, 3, and then 2, 0, 2, 2, and 2, 3, and 3, 0, 3, 2, and 3, 3. And we are good to go. Phew! That was kind of crazy. All right, so I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. If you like what I'm doing, hey, please subscribe. I'm trying to work my way up to 1,000 subscribers. Let's see if you can help me. Tell your friends. Bye.